Have you ever, been chatting with an AI, maybe asking it something, and you get back this really thoughtful paragraph?
Oh, absolutely. It
It's
happens.
almost uncanny, like talking with ghosts in the machine. Nobody's actually typing that reply.
Right.
Instead, it's just summoned up by this incredibly dense, tangled web of numbers inside the silicon. And that right there, that's the core mystery we want to dig into today. How do these billions, maybe even trillions of numbers churn out replies that seem so thoughtful, even creative sometimes?
A deep question.
So our mission for this deep dive is really to explore that invisible arithmetic, how everyday words get turned into something that feels, well, astonishingly like thought. It's a pretty wild journey.
It is. And that journey really, at its heart, it starts with something called embeddings.
Embeddings.
Yeah. Think of them as the fundamental way we turn words into actual points, coordinates in this huge mathematical landscape.
Like a map.
Sort of, yeah.
Mhm.
Imagine language not just as symbols, but as this hidden geometry. And once words become these numbers, these vectors, well, then a large language model, an LLM, it can suddenly navigate that space. It can
Yeah.
stretch it, fold it.
Set it in motion.
Exactly. Set
Yeah.
that landscape in motion. And that's how it creates those replies that seem so coherent, so thoughtful.
That's perfectly put. And this deep dive, it's really custom tailored for you listening. We're going to take let's say, a clear walk, step by step, through each stage of that whole performance. We'll look at why words even need to become math for computers, how these meaning maps get built, how these things called transformers remix that meaning.
Which is crucial.
Totally. And how raw probability somehow turns into flowing prose. And, the big one, where does understanding, like real understanding, begin and end for these things?
And what we still don't know.
Exactly. What mysteries are still out there, just beyond what we can grasp right now? So let's start with that foundational shift. Computers, right, at their core, they only get binary, ones and zeros, highs and lows, digital stuff.
That's their language.
So if you feed a computer Shakespeare, to be or not to be, it just sees, well, a long string of bytes, numbers. It has absolutely zero clue what being or not being actually means,
Right.
not in any human sense.
Right. It's just data, no context, no inherent meaning.
Not at all.
Precisely. So the massive breakthrough came when researchers figured out how to capture what we call semantic relationships.
Semantic relationships, meaning the connections between words.
Exactly. The deep connections, the nuances of meaning. Capturing that in a way computers could actually process and maybe even, well, reason with.
Reason,
Well,
okay?
think of it like this. An AI needs to somehow grasp that king and queen are related in a similar way that, say, cat and kitten are.
Right, the analogy.
And that both those pairs are way more related to each other than either is to something like volcano.
Okay. Obvious to us, but not to a computer initially.
Not intrinsically, no. Before embeddings, it just couldn't make those kinds of leaps.
So how do embeddings solve this geography idea?
Well, the core idea is treating meaning as geography. If every single word gets assigned specific coordinates in some very high-dimensional space,
High-dimensional,
lots of dimensions,
lots. Then closeness in that space literally equals relatedness in meaning. Those coordinates, those are the vectors of numbers, the embeddings.
okay. The numbers are the location.
Yes. And giving a computer that kind of map lets it actually calculate with meaning. It can measure distances between words. It can understand the direction from one concept to another, even angles between ideas.
Wow.
So a sentence suddenly becomes like an itinerary, a route through this meaning landscape, and a whole conversation that turns into a complex path.
That's a really cool way to think about it.
Yeah.
But how do they build that map, this meaning geography? You mentioned eavesdropping. Yeah, it's a bit like learning by eavesdropping, but just on an absolutely massive scale.
Yeah.
Imagine trying to teach a kid a language, right? But you only give them billions of books, articles, subtitles,
No dictionary.
never a dictionary. That kid would eventually figure out that words like, say, river and stream, they must mean similar things.
Because they show up in similar places.
Exactly. Because they keep appearing in similar contexts, similar sentences, not because they look them up. Embeddings basically do that, just industrially.
Okay. Industrial scale eavesdropping. I like it. How does that work, technically?
It generally boils down to three main steps, done over and over. First, the model basically reads everything. It just gobbles up billions, literally billions of sentences from the internet, books, all sorts of text.
Step 1, read it all. Got it.
Step 2, it plays a game. You take the sentence, randomly hides one word and asks its own internal network to guess the missing word.
Predict the blank.
And third, if the guess is wrong, which it will be a lot, at first it tweaks its internal numbers. It just nudges the values in its network slightly, so the next guess for a similar situation is hopefully a tiny bit better.
Learn from mistakes. Constant adjustment.
Exactly. It's this slow, iterative process. And what comes out of that is really quite profound.
Which is?
Words that consistently get used in similar ways, in similar sentence slots, they end up collecting similar numerical vectors. Their coordinates drift together.
Ah, so doctor and physician.
They drift towards each other in this meaning space. But words like peanut and planet,
not so much.
They stay far apart. Their numerical closeness, or lack thereof, reflects how similarly they're used in language.
And you mentioned high-dimensional intuition. That part really bends my brain. We think in 2D, 3D.
Right, we can visualize that easily.
But these things are working in spaces with, what, hundreds, thousands of dimensions?
Sometimes 768, sometimes 2048, even up to 16,000 dimensions or more in some models.
16,000? Why so many?
It's to capture all the incredibly subtle nuances and relationships between words. Think of all the different ways a word can be used, all the slight variations in meaning. You need that huge dimensionality to give every concept enough room to have its own unique location and relationship to others.
Okay, it allows for complexity, but you said they can do algebra with meaning in there? That sounds wild.
It really is. This is where some of the magic seems to happen. You can take the vector for woman, right, and then you find the difference, the direction, between man and king.
Okay, it's that relationship.
Add that difference vector to woman, and where do you land? Mathematically, right near the vector for queen.
Whoa, seriously?
Seriously. Or think about verb tenses. Moving from the vector for talk to the vector for talked is a consistent little hop, a specific direction in this space that basically means past tense.
So the geometry captures grammar, too.
It captures these relationships, yes. And it's not just single words. You can embed whole paragraphs, bundling complex thoughts into a single vector. That's a big part of why modern search engines are so much better now.
Right. They find passages that mean what I'm asking, not just ones that have the same keywords.
Exactly. The search is happening in that meaning space. And the most amazing part, these tricks, these relationships, like king minus man plus woman equals queen, they are learned.
Not programmed in.
Not programmed. Nobody explicitly coded that rule. It just emerges naturally from the statistics of how words are used across billions of examples. The geometry of meaning just falls out of the data.
Mind blown. Okay, so we have these amazing meaning vectors. Where did they go next? You mentioned transformers?
Right, so now we have this rich garden of vectors, these numbers representing words and meanings. We feed them into the next crucial piece, the transformer network.
And this is where the meaning gets remixed.
Right. That's a good way to put it. This is where the context really gets processed. And the key ingredient, the secret sauce, as one paper famously put it, is attention.
Attention is all you need. I've heard that phrase.
That's the one. And attention here is a specific mechanism.
Yeah.
It lets each word in a sentence dynamically. We'll peek at every other word.
Peep.
Yeah, look at every other word and decide, how much should you matter to my meaning right now?
Okay, give me an example.
The classic one is, the trophy doesn't fit in the suitcase because it is too large.
Okay.
What does it refer to? The trophy or the suitcase?
Ah, the trophy's too large.
Right. But how does the computer know? Attention helps the network see that it is strongly connected to trophy, not suitcase, based on the surrounding context and probably world knowledge learned during training. It weights that connection higher.
So it figures out the pronoun reference through this attention mechanism.
Exactly. It weighs the relevance of all the other words to understand the current word in its specific context. Absolutely crucial for getting the meaning right.
And mathematically, how does that weighting happen? Is it complicated?
It involves some clever math, yeah. Things like dot products between vectors and functions like softmax to turn similarities into focused weights. But the real power isn't just one step.
It's layered.
It's layered. You have dozens of these attention layers stacked up like pancakes. Each layer refines the understanding based on the layer below it.
Pancakes of attention. I like it.
It allows the network to weigh context at many different scales simultaneously. From local grammar, like word order, to sentence-wide themes, even tracking ideas across a whole paragraph.
And I read something about stacking and skipping. What's that?
Ah, yes. So you have these stacks of attention layers, dozens deep sometimes, but crucially, they're also residual connections. Think of them like express lanes.
Express lanes.
Yeah, they let information from earlier layers literally skip some of the intermediate layers and get added back in further down the stack.
Why would you do that?
It's vital for memory. It helps the model retain information from the original input and earlier processing stages. It stops important details from getting diluted or lost as the signal goes through all those transformations.
Okay, keeps the original signal strong.
Precisely. So the end result is this deep, complex pipeline. It takes those raw word embeddings we started with and gradually transforms them into much higher order representations. It moves from just basic word meaning towards phrase meaning, sentence meaning, and sometimes you can even argue towards understanding the speaker's intent.
Wow. Okay, so that's how it understands context. But how does it actually write? How does it generate the text we see?
Right, the generation part. All that complex processing we just talked about, it's ultimately trained for a surprisingly simple game.
Another game.
Kind of. The game is, given all the words I've seen so far, guess the very next token.
Tokened, not word.
Often token, yeah. A token isn't always a whole word. It could be a common word like the or cat, or it might be part of a word like run and then ing, or even just punctuation, like a comma or a period.
Why break words up like that?
It's more efficient and flexible. It lets the model handle rare words it hasn't seen often, or even new words by breaking them into pieces it does know. And it keeps the vocabulary size manageable.
Okay, so it learns to predict the next token.
Exactly. After reading and predicting across billions and billions of these text sequences, the network basically learns a giant probability map. For any given sequence of tokens, it knows which tokens are most likely, statistically, to come next.
Like if I type, "the cat sat on the new art," it knows Matt is super likely.
Super likely, but also chair, roof, sofa, each with a different probability based on everything it learned from the training data.
So how does it choose? Does it just pick the most probable one?
Sometimes it does. That's called greedy decoding. But often it works more like, well, rolling loaded dice over and over again.
A loaded dice.
Yeah. The probabilities tell the model how to load the dice for the next token. Then it rolls them. Technically, it samples from that probability distribution. It might pick the most likely token, or it might pick a slightly less likely but still plausible one.
Why not always pick the best one?
Picking the absolute most likely token every time can lead to very repetitive, boring text. Sampling introduces a bit of randomness, making the output feel more natural, more creative sometimes.
Okay, so it picks a token.
It picks a token, adds it to the sequence so far, then feeds that new, slightly longer sequence back into itself as the new context.
And predicts the next token.
And predicts the next token and repeats. Token by token, it builds the response.
That's fascinating. It's just predicting the next piece again and again.
Fundamentally, yes. A very sophisticated prediction, but a prediction nonetheless.
But when you see the result, especially a long, coherent answer, it really looks like thought from the outside, doesn't it?
It absolutely does, and there are reasons for that. One is context lengthening. Modern models can track the conversation, the context, over thousands of tokens. That's like remembering many paragraphs of text.
So it doesn't forget what we were just talking about.
Exactly. Its attention mechanism lets it dynamically focus on the relevant parts of that long history, kind of like a flexible, short-term memory.
Okay, and I heard about temperature knobs.
Right. Temperature is a parameter developers can tweak during generation. Think of it like a creativity dial.
Creativity dial.
A low temperature makes the model play it safe. It sharpens the probability differences, so it strongly prefers the most likely common next tokens. You get sensible, but maybe cliche, predictable text.
Okay, safe mode.
Right. But a high temperature, that flattens the probabilities. It makes the model more willing to take risks, to choose less common, more surprising tokens.
More creative, potentially, or maybe nonsensical.
Both are possible. It increases the chance of novel connections, but also the chance of going off the rails. It's a trade-off.
Interesting. So even with all this complexity, the attention, the layers, the temperature, you're saying the core mechanism is still statistics, just predicting what word comes next based on pattern.
At its absolute core, yes. It's statistics of co-occurrence, what words tend to appear together, in what order, in what contexts. But, and this is a huge but, it's operating in an astronomically vast combinatorial space. It's not just learning A follows B, it's learning incredibly complex high-dimensional patterns about sequences, structure, style, even implied relationships. Patterns of patterns of patterns.
So some statistics, but on a scale and complexity that starts to look like something else.
Precisely. It looks like understanding or reasoning from the outside.
Which, okay, brings us right to that massive question, the elephant in the room. Does the model actually understand any of this?
Ah, the big one. Yeah, the philosophical minefield.
Where do you land on that, or where does the field land?
Well, there isn't really consensus, but a pragmatic view is emerging. We can see different levels of behavior. There's what some researchers call System 1 behavior.
Like Kahneman's System 1 thinking, fast, intuitive.
Exactly. Rapid pattern completion. You start, roses are red, violets are, and the model instantly says blue. It's pulling on strong, learned associations. Very fast, almost reflexive.
Okay, that feels like pattern matching.
Then there's something maybe like System 2 light. This comes from techniques like chain of thought prompting.
Where you ask it to show its work.
Right. You nudge the model, think step by step, and forcing it to generate those intermediate reasoning steps often makes it better at complex problems. It's like it's simulating reasoning, even if it's still based on predicting likely sequences of thought-like text.
Simulating reasoning. Interesting distinction. What else?
And then there's tool use, giving the model access to external tools via plugins or APIs. It can look up current facts, run code, query a database.
Like how we use Google or a calculator.
Exactly. It extends its capabilities by using external resources, mimicking how humans offload cognitive tasks.
Okay, so these behaviors, pattern matching, simulated reasoning, tool use, they definitely feel cognitive, don't they? They're flexible, coherent.
They absolutely do feel cognitive. The models can talk about almost anything, stay on topic, generate sensible, often helpful text. But, and this is the crucial insight many researchers keep coming back to,
Here it comes.
they lack experience, embodied experience. They have no sensory input from the world, no body, no emotions in the human sense. It's all just derived from patterns in text, textual echoes of human experience.
Sure, it can talk about rain.
But they've never actually felt wet. They haven't experienced the world they describe. Their knowledge isn't grounded in the physical or emotional reality we live in.
That feels like a pretty fundamental difference.
It likely is.
And this is where it gets really interesting for me, because even with all this progress, all this engineering, it sounds like there's still a lot we just don't understand about how they really work deep down.
Oh, absolutely. That's definitely the case. Even the top engineers building these things will readily admit that some of the leaps in capability, how they suddenly get good at certain tasks, it's still poorly charted territory.
Flaky areas?
Definitely some foggy areas we're actively trying to map.
Like what are the big unknowns?
Well, first there's interpretability. Big one. We can poke around inside the model, look at which artificial neurons light up when it processes certain things.
See what's active.
Right. But translating those patterns of activation, those spikes, into clear, human understandable rules, that's incredibly hard. Why does this specific pattern across thousands of neurons suddenly make the model bring up, say, medieval alchemy?
We can't easily trace the logic.
The precise causal chain is often really murky, which makes it hard to fully predict behavior or guarantee safety or even debug effectively when things go wrong.
Okay, interpretability is tough. What else?
Then you have emergent capabilities. These are abilities that seem to just appear almost out of nowhere when models get bigger or are trained on more data.
Like what kind of abilities?
Things like performing multi-step arithmetic reasonably well, or generating code, or even showing hints of understanding what other people might be thinking theory of mind. These things often weren't explicitly trained for.
They just emerge.
They seem to, yeah. Once the model crosses a certain threshold in size or data, these skills pop up. And nobody really predicted the exact tipping points.
So the big question there is, are they just weird side effects of scale? Or are they hints of deeper, more general principles of intelligence starting to form?
That's exactly the debate. We don't really know yet.
Okay, what else is foggy?
Long-range generalization. Models can be amazing mimics. They can write a paragraph that sounds exactly like Tolkien, right?
Yeah, they're good at style imitation.
But then you ask it a simple logic question, maybe one that requires carefully tracking information across slightly more sentences than it's used to, maybe just beyond its core context window. And it just completely flubs it.
So it's brilliant in some ways, brittle in others.
Exactly. Why can it master complex style but fail at seemingly simpler reasoning tasks that require tracking things over a slightly longer distance? We don't fully understand the limits of its generalization.
And you mentioned bias earlier.
Right. Bias and alignment, this is huge. The models learn from the internet, right? And the internet is, well, it's a messy reflection of humanity. Full of biases, stereotypes, misinformation, toxicity.
Garbage in, garbage out.
To some extent, yes. The embeddings themselves soak up these societal patterns from the data. The models learn to reproduce them. and trying to fix that to align the model with human values using techniques like reinforcement learning from human feedback, RLHF.
That's where humans rate the AI's answers.
Yeah, providing feedback to steer it, it helps, definitely.
Yeah.
But it's widely seen as more of an art than a solved science right now. It's hard to stamp out all the bad stuff without also making the model, dull or overly cautious, or even introducing new subtle biases from the human raters.
Tricky balancing act.
Very tricky. And then, of course, there's the cocktail party question.
Consciousness.
Consciousness. Is there anything actually going on inside?
Yeah.
That's mostly philosophical speculation at this point, but it's definitely out there in the fog.
Okay, so lots of fog. But presumably people are working on shining lights into it. You mentioned frontiers.
Absolutely. It's not all mystery. Researchers are pushing hard on several fronts, really trying to bridge the gap in our understanding and capabilities.
What are those main frontiers?
We can think of maybe 4 big ones right now. First is that mechanistic interpretability work we touched on.
Trying to map the circuits.
Exactly. It's like painstakingly dissecting a really complex clock to figure out exactly how every single gear and spring contributes to the final ticking. Trying to trace specific behaviors back to specific circuits inside the model.
Hard work, I imagine.
Incredibly detailed work. Second frontier, multimodal grounding.
Multimodal, meaning more than just text.
Right, like adding eyes and ears to the chatterbox. Connecting the language models to images, video, audio, maybe even robotic actions. The idea is to help anchor the abstract concepts learned from text into something closer to physical reality.
Grounding the words in sensory data. Makes sense.
Third, modular hybrids. This is like hiring specialized experts to work alongside the big LLM.
How does that work?
You combine the LLM's general language skills with other systems that are maybe better at specific things, like strict logical deduction using older symbolic AI methods, or accessing structured knowledge from a database, patching the LLM's weaknesses.
Like building a team of specialists.
Kinda, yeah. And the fourth frontier, maybe neurosymbolic feedback.
You're symbolic.
It's trying to bridge the gap between the neural network's pattern matching and more structured symbolic reasoning. One idea is like teaching through Socratic debate, having models, or models in humans, critique and refine each other's reasoning processes to arrive at more robust, verifiable answers.
Interesting. Using debate to improve reasoning.
Exactly. So each of these frontiers is actively chipping away at the fog, pushing the boundaries. But of course,
they introduce new problems.
They often introduce new puzzles and challenges too, like grounding models with real-world data raises all sorts of tricky privacy issues, for instance. It's ongoing work.
It really feels like we're building something incredibly powerful, even if we don't fully understand every bolt and wire yet.
That's a good way to put it.
So bringing this back down to earth a bit, what does all this, the embeddings, the transformers, the probabilities, the mysteries, what does it mean for you listening? How is this showing up in everyday life?
Oh, it's already everywhere. These ripple effects are constant, even if you don't always see the underlying tech.
Like where?
Well, think about modern search engines. Google, Bing. They're not just matching keywords anymore. When they give you a direct answer at the top or find that perfect paragraph in an article, that's often embeddings at work, matching the meaning of your question to the meaning of passages in their index. It's meaning-based search, not just keyword overlap.
Ah, okay. That's a big one. What else?
Email autocomplete. You know, when Gmail or Outlook suggests the rest of your sentence?
Yeah, sometimes spookily accurate.
It's not just predicting the statistically most common next word. It's often sampling from a model that subtly learned your personal writing style, your language fingerprint from your past emails.
So it sounds like me.
It tries to, yeah. Using embeddings trained or fine-tuned on your data. Or think about language learning apps like Duolingo. When you type a reply in French or Spanish and it says close enough, even if it wasn't perfect.
Yeah, it gives partial credit sometimes.
That's embeddings again. It measures the distance between the vector for your answer and the vector for the ideal native phrase in that meaning space. If you're close enough, you get credit. It understands semantic similarity.
That's clever. Using the meaning map for grading.
Exactly. And it's even moving into really complex science. In drug discovery, some researchers are treating molecules like sentences. They represent chemical structures using embeddings.
Molecules as vectors?
Yeah. And then they explore the mathematical neighborhood around known drugs to find new, undiscovered compounds that might have similar desirable properties, using the geometry of molecular structure to predict function.
Wow. From email to drug discovery, that's quite a range.
It really is. The applications are spreading fast.
So understanding this core trick, then turning concepts into coordinates, into math that computers can work with, that seems pretty important for everyone.
I think so. Because it helps you as a citizen make sense of the bigger picture. When you hear debates about AI safety or copyright issues with AI-generated art or text, or how AI might displace jobs,
Yeah, those are huge topics right now.
knowing a bit about how these things work helps you evaluate the claims. Is the AI actually copying existing work verbatim? Or is it surfing semantic gradients, as some put it, navigating this meaning space to generate something novel but maybe derivative?
Though sometimes it does copy verbatim too, right? If that was in the training data.
It absolutely can, yes, especially for things it saw many times. But understanding the difference between that kind of memorization and the more generative process shapes how we think about creativity, ownership, and ultimately the laws we might need.
It gives you a framework for thinking about it critically.
Exactly.
Man, what an incredible journey we've taken today. Seriously. From just why words even need to become numbers for a computer,
The fundamental limitation.
to how these meaning maps get built through that massive eavesdropping,
Billions of sentences.
how transformers use attention to remix meaning based on context,
The pancake stack.
the pancake stack, and then how simple probability rolled over and over turns into this flowing, often incredibly thoughtful prose.
It's quite a sequence.
It's truly remarkable stuff.
It really is. And, there's a deep philosophical insight kind of baked into all this, something these models demonstrate really vividly,
Which is,
that so much of meaning is relational. A word by the company it keeps.
right, context is king.
LLMs just push that idea to its absolute extreme. They build this abstract map, this topography, where the distance between abstract concepts like, say, joy and sorrow is actually measurable, where adding the vector for fork to the vector for breakfast nudges the result towards pancake.
The map talks back.
The map talks back. But it's still crucial, always, to remember. The map is not the territory.
It's not the real world.
Right. Their understanding, impressive as it seems, still falls short of that messy, embodied richness of actual lived experience. Like we said, they talk about rain, but they never feel wet.
They can mimic empathy.
Because they learned the patterns of empathetic language from novels and conversations in their training data. Not because they've actually felt love or loss or heartbreak themselves. It's an echo, not the source.
So where does that leave us? Standing on the shore, looking out.
That's a perfect analogy, I think. We're standing at this intellectual shoreline. Behind us, we've walked a pretty clear path, the one we've traced today. Raw data becomes embeddings.
The meaning map.
Those feed into attention mechanisms and transformers,
Context remixing.
which output probabilities,
The loaded dice.
leading to the generated replies you see on your screen. That path is becoming clearer.
But ahead.
Ahead lies this vast ocean of unanswered questions, the fog we talked about. Which specific circuits fire when a model genuinely seems to intuit irony or sarcasm? Will adding vision and hearing and action truly fuse these language vectors into robust world models? Can we ever guarantee alignment for systems built purely on statistical patterns from human text?
Big questions remain.
Huge questions.
The marvel of it all is just, it's undeniable. But the mystery definitely endures, it feels like. With all powerful tools, these LLMs are these incredible levers, right? They amplify our own insight, but sometimes maybe they amplify our confusion too.
That's very well put. They reflect us, warts and all.
So maybe knowing the parts we do grasp and acknowledging the parts we don't yet grasp, maybe that's the vital first step, the step towards using them wisely.
Responsibility starts with understanding the limits.
Exactly. And perhaps one day, that understanding might help us close the gap just a little bit more, the gap between this amazing carved-in-silicon statistical mimicry and that uniquely human spark, the thing that invented language in the very first place.